Hello and welcome to week 5. In this week, we'll talk about TensorFlow and how to accelerate and different interoperability that is available in TensorFlow and other frameworks. So here in this week, we will divide this entire lecture sessions into 5 segments. So in the first segment, we'll talk about the execution models. You know, the PyTorch has already been covered and we have seen the complete training pipeline, right, and also evaluation pipeline or validation pipeline. We have talked about in great detail about the tensors, so I will not repeat exactly what tensor is. However, tensors will be one of the key ingredient of any framework that will be working in the area of machine learning and AI. So here in this TensorFlow execution model, obviously we will talk about first the TensorFlow and what are the different performance basics that we need to take care in the segment of this TensorFlow, because TensorFlow is end-to-end framework that will come into, and obviously in this segment 2 that will proceed with the optimizing, because optimization of input pipeline is most important. As in the PyTorch, we have seen that data pipeline, which is input, preprocess, train, load, and essentially that will repeat. So this pipeline will actually transfer data from different memory hierarchy that we have seen in the first lecture. So in this segment, we will talk about the best practices for optimizing the input pipelines with tf.data, which is basically the data pipeline framework in the or library in the TensorFlow framework, and then we'll proceed with the graph execution and TensorFlow optimization. So in this segment, we will talk detailed the graph execution, which is essentially the static compile graph that will be formed, that we will actually see how it is formed in the segment 1. And we will take it forward into segment 3 and we will see several other optimizations and best practices while making this entire training pipeline. In this segment 4, we will see the XLA compilation, which is very important in modern day AI algorithms, and also we will see other interoperability available in this framework. So to start with the segment 1 and other segments, in the end of this week we will understand the eager and graph execution modes. So these two execution modes we will talk about because these two execution modes are available in TensorFlow, which will be used in different levels of AI algorithms, because at some point of time we need Pythonic way of execution, that is essentially your eager execution, and sometimes we need to compile statically and get the best optimized model execution graph, and that's the two differences that we will see, and we will understand exactly what they are and how we have to use, and exactly what are the different points that I am talking about where to use it. And obviously we will see the computation graphs in terms of performance. So always we'll end up with optimizing performance, right? So we are talking about how to get best out of these optimizations, how to speed up my complete pipeline flow, how to accelerating my AI workload that I'm going to deploy in both the training and testing pipeline. So here we will see that few decorators we will talk about. tf.function is one of them, and autograph, which is the graph optimization. So if you remember the autograd mechanism or the complete machines that is available in the PyTorch, which were doing the gradient computation automatically, basically the backward pass was doing the gradient computation, which is done by the chain rule computation, right? So that we have seen in the PyTorch. The equivalent of that we will see in the TensorFlow, but there is some differences and different use cases that also we will see, and XLA compilation flow, and we will be understanding the model transformations across different frameworks using ONNX. So all these important topics we'll be covering. So in this segment, we'll talk about the tensors and what are the operations that are available. Talking about TensorFlow, TensorFlow was released in 2015 by Google Brain team. You remember the brain float data type, right? So now you can connect to these different libraries that will be available in this TensorFlow as well. Then these, obviously that was very early release in 2015, and in subsequent releases the complete framework got better and better. So nowadays we have 2.x version, which is basically the version above 2.0, and this framework supports the complete executions in CPU, GPU as well as TPU, tensor processing unit, and you know tensor processing is widely used in Google data centers, right? And obviously we will have the distributed execution support also. Okay, two levels of APIs are used here. So high level API, which is the Keras API for rapid model building, usually used for quickly prototyping and seeing the training how it is going. And low level APIs are available like tf.tensor, tf.variable, tf.gradient tape. So different low level APIs are there, which gives you fine control over the complete model definition. So here we are mainly seeing how we can get the most out of it, right? So that means we have to talk about the low level APIs, because low level APIs will give you better control over what exactly you are trying to achieve, right? And obviously get greater flexibility in the development process also. High level APIs will be just to see what is off the shelf that is available and basically take it and plug and play. So this will be rapid prototyping, but low level will give you flexibility as well as better performance. So now you know what are the APIs that are available in this TensorFlow framework, which will be used across this entire week lectures. Few core concepts we'll talk about, the tensors as well as the multidimensional arrays, tensors in the form of their different operations that are available, and then we will also talk about basically on the automated complete flow. Okay, so TF serving, TF lite, tf.js, tfx, so these are different ecosystems that are available for different deployments. So deployments are also are part of TensorFlow framework, because this gives you this end-to-end deployment framework, right? So all these built-in support and rich ecosystem makes this TensorFlow a complete framework. So basically most of the production environment nowadays in the organizations, they use this TensorFlow for their production grade AI deployments. We'll first talk about the eager execution and graph execution a little bit here. We'll just touch upon the concept, and we'll talk about the graph execution and optimization in great detail when we'll come to the segment 3. So eager execution, as you are seeing here, the Pythonic way of executing. That means line by line. We are working in Python interpreter. So by default, we are executing line by line. So operations are executed immediately, line by line, like regular Python in this mode. So if you are using any version tf2.x, so basically you are using eager execution. It's easy to debug because you know exactly what should be executing at what point of time. So you can give prints, you can use Python control flow directly to see exactly how this control is flowing one by one line, and essentially print tensors, what are their values at a given point of time. So that's how it's easy to debug also. And one such example is result equal to, let's say, tf.mul. Here we are multiplying two tensor, which are matrices A and B, we are result in this variable. Okay, so now this line, when I just execute, that means this runs instantly, there is no waiting. So basically this line comes, it will see the values of AB, that is from the memory, and it will execute. But drawback is cannot be serialized easily because we exactly do not know what are the operations we are going to next execute, right? So if there are any opportunities of optimization available in the next, in this line we are not able to perform because we have already executed that particular line. So that's why graph execution in TensorFlow gives you better performance. We'll see in performance wise, but as I said that the line by line execution is very hard to optimize, easy to debug. Graph execution on the other hand will build symbolically. First the entire code it will just see, and it will then execute this entire computation graph which is defined in this Pythonic way of coding. So it enables whole graph optimizations, and so if I have some operator defined before and there are opportunities to fuse them later in my code section, that I will be able to do, like operator fusion, then constant folding. So if I have already declared few constants, if they need to be merged together or not, based on my execution pattern, it can analyze the entire flow of execution and then it can apply those optimizations, and then better performance can be achieved. So if I want to have better optimization, I will use graph execution, which is available from 1.x, so basically earlier way of executing, but the modern versions of TensorFlow use this decorator which is at the rate tf.function. So we'll use this in the code also, we'll see how to use that. So it's not exactly what to use at what point of time. Basically you have both the choices of execution. You have Pythonic way of execution, you have graph execution as I was doing before, maybe version 1.x. We can also seamlessly convert eager code to graph with a single decorator function, tf.function. So this usually used for production. So first we code eager mode, we debug, everything is fine. Now we just put the decorator over the functions that we are trying to, let's say, optimize better. So let's go to the code section and try to see how it is exactly happening. So before that, first few abstractions we are looking at. As I said, tf.constant, you can see here we are defining tensors here. Different ways of defining tensors are there. Like here we are defining a scalar value with this data type of int32. So you can see here we are using tf.constant, which is defining a constant value in scalar mode, and here we are defining vector because we have now this dimension, right? So basically we have 3 dimension here and we have this value. So basically this is a 1D array, but the multiple values can be added, and basically we are making a vector here, right? So this is a rank 1 vector, this is rank 0 because it's a scalar value. Here we have list of lists type of data, so which is basically matrix 2 dimension. So I have first dimension here which is the row and then column basically, right? So this is another way of defining the matrices. And if we go beyond more than 2 dimension, obviously we can initialize exactly how we initialize the tensors before, but we can also add the size, right? So let's say I have tf.zeros, I want to initialize zeros into my 3 dimension of matrices, so basically batch of matrices. So this is the rank 3 tensor that we have here, which has 2 batches of 3 by 4 matrix, right? Now here we should mention the difference between the PyTorch tensor and the tensors that we have seen so far, that is defined using this TF TensorFlow APIs. Now what are the differences? The tensor that we have seen in PyTorch, they are mutable, okay? So we have seen the in place operations, right, with underscore after the operations, right, which is overwriting the value of the tensor by after the operation. So x plus equal to x something, right? So that's how we did it. But here the tensors are immutable, so that means in place operations are not available. So if I want to let's say re-evaluate or reassign the value here, this will not expect, because here we have defined tf.constant and this is immutable, and essentially this will throw an exception and we can catch it and we can say that this is exception. Okay. Now we can have mutable tensors here, so we can have a flexibility over the definition of tensors basically. So here we have defined with dot constant, dot zeros. You can initialize tensor with immutable structure, but if you want mutability in the tensors, we have to use variable. Okay, so tf.variable here, similar way of defining the data, and we can see that the name is w. Obviously we will use the variable tf.variable for the state where we need to let's say update the values for, let's say in the training phase for gradients, right, for the weights activations. So now here weights are assigned or weights are declared or defined with this tf.variable, which gives the mutability in the weights, which we will be let's say using for gradient computation and updating the weights. Basically we have to update the weights. That's the key target for the training, right? So we have to update the weights, for which we are trying to minimize the loss. Okay, so NumPy interoperability, so I can convert NumPy to TF. So this is NumPy array and we can convert it into an immutable tensor here, and we can go vice versa. So we can go from TF to NumPy as well by using .NumPy. Okay, so here are the outputs that you are seeing, and core operations, you have the add operation, multiply. So here you can see that we are doing the operation, we are converting to the NumPy array and printing it. It's in CPU happening so far, right? Then we can have some reduction operations, so element wise sum, column wise mean, right? And then max of all the elements between all the elements of A. So if you have seen the A's value, so we have defined A as tf.constant here. Okay. Okay, so similar to the PyTorch, that reshaping, resizing, as well as the different shapes and sizes we have seen, you should practice also how to use reshape function, flattening the tensors, column vectors, extraction, and so on and so forth, right? So all these operations are almost similar to this PyTorch equivalent. Okay, so tensors, as I said, will not go again deeper details of tensor reshaping and resizing, but you understand the concepts from PyTorch, but the usage you are seeing here. Okay, so now automatic differentiation with tf.gradient tape is the core of training pipeline, because we have seen the autograd machine in PyTorch, right? Now tf.gradient has bit more flexibility if you see from the deployment point of view, because autograd was kind of automatically computing from the backward pass. So when we apply, we have less control over which are the functions that we are trying to achieve. So they are based on tensor gradient, where which tensors are having gradient tracing true. Based on that, which operations they are flowing through, that will be considered in the autograd machine. Here it's a bit different, because the tf.gradient tape will record all operations executed inside it. So you can think it of as a recorder, right? So which will record all the operations that are happening inside this tape, and when you do the backward pass, these functions will be auto-graded with the chain rule calculus. Okay, so here let's see some example first, right? So x equal here tf.variable, as I said, we'll use tf.variable for the parameters, right, where we apply the gradients and try to update them. So here x is scalar here, right? So here first we are saying scalar gradient. Okay, now this section is definition of the gradient tape as tape which is taking this particular function, which is basically fy, the function says the computation of y, which is equal to x square plus 3x plus 2, which function we are trying to. So basically we are trying to calculate dy dx, right, where y is function of x here and dy dx is equal to tape dot gradient y x. So this is the normal gradient method which is called over this tape, which recorded what exactly the function for which I am differentiating for. And essentially when we call this particular tape dot gradient, we are trying to do dy dx for x equal to 3 at x equal to 3, right, and we are just printing the value here. Now this will be applicable similarly for the multivariate variable gradient as well. Here x1 is one variable, here x2 is another variable, both are tensors, can be scalar, can be different rank also, we have seen before. Now this particular tape is defining which is the function. Now we can see that this is a multivariable function which has x1, x2, and now z is the target function for which we will be applying the gradient for. So now you can see that these two variable is basically doing the delta z delta x1 delta z delta x2, and we are trying to tape the gradient. So tape dot gradient over z, and we are trying to differentiate z for the changes for x1. So we can see that x1 and x2 are defined in this particular list for which I am applying this gradient for, right. So now comparing this to this neural network, you have the loss function which you are computing and all these weights and biases for which, so we will be trying to differentiate, we are trying to get the gradient of the loss function with respect to all these variables, right, multivariable, right. So this neural network is basically this multivariable function, right. Now the persistent tape is one such mechanism for which we will record or which we will see the difference between the PyTorch and gradient here with respect to zero bias or zero gradient or zero grad, right. So what you did in PyTorch, we did apply zero grad. So when we apply the gradient, and if we do not do the zero grad, so we will be accumulating the gradients over each iteration in the training phase, right. So each time the backward pass will happen, the gradients will get accumulated, right. By default we had to forcefully zeroed out all the gradients because the next gradient will be computing based on the new forward pass value loss function, right. Now in this TensorFlow, right, here the call this tape dot gradient, when we call this tape dot gradient means the gradients will be zeroed out. So the record, whatever we have recorded the gradients, it will forget the values that it had recorded. So this applies the equivalent zero grad by default, okay. Now sometimes we need to keep the gradient values, because for that case we need to have persistent tape, because we want multiple call for this particular gradient over this tape, right. Tape is recording the function values for the values that we are assigning here, right. So these are the multivariable function. Now let's imagine x is one such variable here, scalar, and now I am defining two functions here, f and g, which is x cube and x square. Now you see here two functions are there, and now I want to, so imagine for multi-loss cases in the neural network training scenario, I have two losses, I have three losses, I have four losses, right. So here I have two functions for which I want to calculate the gradient with respect to x here, right. So now when we call this tape dot gradient for this function with respect to x, tape will forget, right. But if I make this persistent equal to true, that means the tape will keep record of whatever the values of f and g has been calculated for, and it will actually see the next gradient call as new call with the value of x equal to 3, right. So 2x equal to 6, and if I do the gradient apply, so dg dx, so I'll get expected 6, right. And by default, if I do not give this persistent equal to true, essentially it will forget whatever it has recorded with each gradient call. Now we can do a del tape which will delete the record. So now if I have multi-loss, single loss, so I have better control over the functions that I am applying, for which I want to calculate the gradient with respect to the weights and biases, and this gives better control. But obviously there also you can do the same, but you have to see where exactly you can do the zero grad apply and so on and so forth, that we have seen. So I am bringing that analogy of PyTorch because you have already learned that, and basically it will be easier for you to grab what exactly you have implemented and what we are implementing in TensorFlow framework. And you can see this output as expected, right? Okay. So with this we'll conclude this session, and in this next section we'll talk about this eager execution, graph execution, as well as the data pipeline in detail, okay, and how we can extract the performance from the eager execution in the graph computation in TensorFlow framework, okay, and also the data pipeline for which we are giving input from the source data to the training pipeline here, okay. So here in this TensorFlow data, which is tf.data that we have talked about in the introductory slides, that works as a pipeline, right. So here we'll talk in detail the pipeline and how to make overlap of subsequent pipelines. Thank you.